So we've got a balanced chemical equation. Which substance do we have two pieces of information for? Right? This one. Okay. So you got to calculate moles. Because you're doing formulas.
How do we know we have two pieces of information?
One piece of information, two pieces of information. One and one make two. Okay? If I don't give you the molar mass, I'm assuming you know how to get molar mass.
I do know how to do that.
Perfect. Then we are off to the races. It's a slow horse, but as long as it finishes. Okay, so N is mass divided by molar mass, which is why I put mass on top. Then the molar mass, because then it's just the top number divided by the bottom number. Right? So, somebody with a calculator, 0.75 divided by 22.98. And that is 0.03 something else. Okay. So that is moles of sodium. We need to convert that to moles of chlorine so that we have two pieces of information about chlorine. So we use the mole ratio. For every 1 chlorine, I need 2 sodiums. Do you know where I got those 1 and the 2?
Yeah, I think it's from like the balanced equation.
From the balanced equation. Do you know why chlorine went on top, sodium went on the bottom? Trying to find chlorine, so this is going to cancel.
So you just divide by 2 then?
Yeah. Now I have moles of chlorine and molar mass of chlorine. I can calculate mass. Right? I've got this and I have this. So this will give us our grams of chlorine if it was just a straight off reaction. However, the question asks for 10% excess. So you're going to multiply your answer by 1.1. Because that's 100% plus the 10%. Okay? All right, so now you know how to do that question, the traditional mole equation. So you take the actual divided by theoretical, and you times by 100%. Okay. You're going to do a lab like this. You're going to be massing a precipitate or a solid that's produced, and you are going to then compare it to how much you expect it to get. And if this was a university lab, your grade would depend on how close you actually were to 100% yield without going over. In university, there's precision, there's accuracy, and then there's percent yields. And all of these are things you're going to get graded on as part of your lab marks. So if you're trying to hit a target, you do an experiment and you calculate a value in your experiment. There's a theoretical value, an actual value that we know. Your lab TA will make a judgment. You'll calculate your percent accuracy, and then your marking scheme will be based on how close you are to being on target. When I was a first-year lab demonstrator, I think less than 2% got you full marks. Over that, you lost marks. My grade 12s just did an experiment. If they got less than 10%, they got full marks. If they got higher than 10% error, they got half a mark. And it's because they did something wrong in their experiment that their values were so far off what they were actually supposed to get. So it has to. This is where it comes into play. Are you actually paying attention?
So what would be the possible errors that
Well, let's talk about that. What do we call those things? Sources of error. What can actually affect? So let's take a look at this. What could be a reason for something being you got more than you actually should have got? Braden?
Maybe you didn't measure everything there.
Is that a mistake or is that a source of error? Is that something you could have controlled? Yeah. So that's actually not a source of error. Yeah?
like usually these solutions are not good. Like remember the last time when we tried to get precipitate and weather precipitate, the solutions were either older.
Maybe you didn't make your product, right? So let's say you've got a solid that precipitates out of solution. How are you going to measure the mass of your solid? How are you going to figure out what mass of your solid you produced? We just did an example where we had aluminum in copper 2 chloride. We made copper and aluminum chloride solution. How would you actually mass the amount of copper that you made? You'd measure it on what? The thing that we use for the gum. The scale or the balance, right? How are you going to get that copper out of that solution?
You put the solution, you press tar, and you put this.
Everything's together in a beaker.
Maybe you could evaporate.
Maybe you could evaporate off the liquid or separate it somehow. But then what would you have to do? Think about your gum.
Try it out.
You got to dry your product, right? You've got to dry your products in order to mass it. So why might it still be over 100%? How can you tell if something's completely dry or not, though, right? if you've got clumps of something, let's say your product is a powder. You've got clumps, your neighbor has a powder, yours isn't dry because it's clumped together. So you do have to actually kind of break it up in order to let it dry. Now, what color is copper? Think of copper metal. It's kind of an orangey color. Has anybody here been to Ottawa?
Oh.
Yeah.
What color is the Parliament roof? But it's made out of copper.
Like the Statue of Liberty.
What does this mean, this oxidize that you speak of?
It's been reacting with oxygen.
And where's this oxygen? Why can't we get rid of this oxygen? It's in the air.
That's what happens to your liquid as well. You have to remove it from the box. It was still in the box. To check it. Check it in your head. It's off. When you leave it in the box. What color is it?
Now sometimes you can't actually tell whether or not you've made an oxide because it hasn't changed color. Copper will change color. It will go from reddish orange color to a green. How do you know? Let's say this case it was aluminum chloride. You had aluminum metal and it dissolved in copper 2 chloride to make copper and aluminum chloride solution. Have you seen aluminum? Aluminum foil. How do you know that there's not tiny pieces of aluminum in your copper product? It might be shiny, but what happens if it's too small for you to see? Right? Sometimes it is really hard to separate your reactant from your product. So that sometimes happens. So I put aluminum here just to kind of make you think about it. If you can't completely separate out with 100% confidence, you haven't tested this to make sure it's pure copper, right? You don't have a mass spec that you can run it through. So you don't know that you have completely pure product. Okay? Well, great question. What if it's under 100%? Say that again? Missing how? Like it disappeared into space? Okay, so you can't remove all of your precipitate? Perhaps you can't scrape all of the copper out of the beaker, or it's stuck on this rubber policeman that you're using to scrape it out, or it's stuck on the aluminum foil that's in excess because you wanted to make sure you made as much copper as you possibly could. There's one that was for you produce more that can also be for this one. That's impure reactant. Sometimes filler is put in. We usually don't get, in high school materials, we don't get 100% pure. Those are called standards, and they are very expensive. So your aluminum foil that you think is just aluminum is actually not just aluminum. Maybe you couldn't transfer all of your reactants too. If you measure out so much, glassware. My grade 12s just did a lab, and they had to measure out magnesium oxide powder. It's a very soft white powder. Pour it into acid, take the temperature change. They didn't bother to rinse the weigh boat, right? The plastic measuring boat that they put the magnesium oxide on. So they didn't actually deliver the entire mass that they massed out. There's some of it still stuck to the vessel that they were measuring it on. I have to look, see if I've got one. So if you can't deliver all of your reactants, but your math is saying you've used all that, that's going to be a source of error. If you wash it in and it still doesn't come in, then it's an actual source of error. So some reactant is always going to get stuck on your glassware. Can you think of another thing? What are we doing? So let's say we talked about using the balance. What did you notice about the balance when you were measuring the gum? It was touchy. Changed a bit, right? Your balance actually rounds off that last number that you see. When you measure volume, you're estimating that last digit. If it's 22.4 milliliters or 22.6 milliliters. So there is always uncertainty in the last digit of measurements. And this could affect over or under. Okay? Faulty equipment. Okay, what else? I just gave you a whole list.
Reagents were not clear.
Impure reactants, sure. What else?
Product still is left on glassware or?
So, but in this case, we would have gas bubbling out. So perhaps not all the gas makes it to the device that is measuring them. Yeah. But that's basically the same idea. Okay, so some stuck on glassware, etc. Uncertainty in the last digit of measurement. That's going to affect your numbers. Rounding errors are not the same thing. So don't ever put rounding errors. That is a calculation issue. That's an analysis issue. That is not a lab. That is not an experiment issue. Okay? So saying you did the wrong calculations is not a source of error.
That's a you problem.
That's a you problem, yeah. That's a user error.